All right, today we're going to be talking about relative and absolute dating, what those words mean, and how we use them to understand the evolution of life on Earth's history. So we'll start off with a terrible joke about carbon dating. I assume you laughed. Kidding. All right, so to understand the history of life on Earth, we need to understand how to read the rock record, not just the fossils. And the reason for that is understanding the geology behind it can give us clues to what type of elements were around at that time. For example, how much oxygen there was. Or even, if we understand the rock record, we can predict where fossils can be found. So there's 3 types of rocks in the rock cycle: igneous, metamorphic, and sedimentary. Sedimentary rocks are going to be where we spend most of our time this semester. So sedimentary rocks are things like sandstone, mudstone, pieces of sediment from larger rocks that have been worn down, broken down, and then compacted later in different configurations through time. All right. So because fossils can tell us a lot about what life on Earth used to be, we can combine our knowledge of fossils and rocks to understand a better picture of Earth's history. So relative dating. Relative dating tries to figure out the order in which rocks were formed. Most of our geologic time scale, which you probably haven't seen before, and that's okay, we're going to look at it today, was reconstructed this way. So this is the 2018 version of the geologic timescale. On the left bar, you can see the bright yellow Quaternary Neogene. That's where we are most recently. All the way down into that pink on the lower right-hand part, the Hadean, the Archean, that's the very earliest part of Earth's history. So this has actually been constructed using relative dating, and we'll show you what that means. So relative dating is a comparison. What this means is it's not a specific date. For example, Elise is older than her sister. Now, you don't know how old Elise is. You don't know how old her sister is. But you know Elise is older. And this is in contrast to absolute age dating. For example, Fernando is 22. You don't know anything about how old Fernando is compared to his siblings. Fernando could be the youngest, the oldest, who knows. But you know that he is 22. Now, you might be thinking, okay, well, this makes sense, the difference, but why do we use relative dating? That seems not very helpful. Well, it's not always easy to find out the absolute age of something in the rock record. Typically, the older a rock is, the harder it can be to find dates. So we actually can learn a lot about relative dating, and we can learn a lot about the geologic timescale from relative dating alone. We also didn't develop any methods for absolute dating until long after we had figured out relative dating. So today we're going to learn a lot about stratigraphic principles and how we can use them to determine how rocks were formed. So this is another picture of the geologic timescale. This one's more cartoony and cutesy. We can see that there have been changes through time. You see those fossils on the left-hand corner. You see that they get different through time. These were actually understood by relative dating. So we knew stuff that contained dinosaurs were older than stuff that contained humans. Things like that. All right, so stratigraphy. Rocks form in layers. Studying these layers is called stratigraphy. We can figure out age relationships, spatial relationships, so which pieces of rock used to be connected, compositions, so what are these rocks made out of, and origins. Was this rock made from beach material? Was it made from a river? Let's find out. So this brings us to a person called Nicholas Steno. And Nicholas Steno was your classic overachiever. He was really famous in a number of different subjects. Geology was just one of them. But he founded the principles of stratigraphy in the 1600s. So let's go through these. You don't need to know Steno's name, but you do need to know the principles he developed. The first is superposition. So, superposition. In undisturbed rock layers, the oldest lie on the bottom and the youngest lie on top. So let's take an example that's not rocks, because we like rocks, or we like other examples a little bit better. Let's say you start a very strange New Year's resolution. All right, it's still January, you can start starting it. So, on the first day of the year, you throw a newspaper that you have read. Your New Year's resolution is to read 365 newspapers. And you throw it onto the floor. You throw January 2nd's newspaper on top of January 1st. You throw September 30th newspaper on top of this very large stack now, every single day for 365 days. When you come to the end of your year on December 31st, you take a look at the stack you made. So, you have the oldest, January 1st, on bottom, the most recent, December 31st on top. And now this definition says undisturbed. What does that mean? So let's put this back into terms of humans. Let's say the stack of newspapers you have, no one's touched it for months, right? No one's touched this, but you adopt a cat. And cats are notoriously jerks. Let's say the cat jumps on top of the pile and knocks it over. Then it has been disturbed. Will the oldest be on the bottom, youngest on top without exception? No. So in geology, certain things can disturb rock layers. It could be a giant fault from an earthquake. It could be an overturning from a mountain building event. Could be a whole lot of things. Original horizontality. Almost all rock layers are originally horizontal when they form. So take a look at the left-hand column, B. You see the 3 layers, 1, 2, 3. They're laying down horizontally. The one on the bottom is oldest, one on the top is youngest. After that event, something has pushed up those rock layers from behind. This could have been a magmatic intrusion from a volcanic chamber. It could have been a bunch of things. All right? But originally, they form horizontally. And this third one, lateral continuity. Lateral means essentially horizontal in space, and continuity means continuous. So rock layers form in large, flat, unbroken expanses. So that means they form like the left column in C. They form flat, plane features. Over time, that can change. And what you're looking at here on the right-hand column is that change. See, a river has cut through and worn out down the center of those layers. That river came after. All right, so let's move to another scientist. This is James Hutton, a very famous Scottish geologist. He introduced the principle of cross-cutting relationships and something called unconformities that we'll discuss in a little bit. But cross-cutting relationships, a geologic feature that cuts through another, is the younger of the two features. All right, so this may sound a little confusing at first, but it's not. If you take a look here on the right side of this diagram, where A, D, and C are, you see that A is cut off by C, and then you see that D is actually cutting across A and C. So what this means is A is the oldest, C is in the middle, and D is the youngest out of those 3 letters. Obviously, we've got other stuff going on here. But another way to think about this is if you have a pair of scissors and construction paper, you know that the construction paper existed before we put cuts into it. Say you cut the construction paper in half. You know that the construction paper existed before being cut. It's the same type of idea. All right, and now we've got the principle of inclusions. This is Charles Lyell. He is a major supporter of Charles Darwin. He was a major supporter of Charles Darwin's science, geologic interpretations, and obviously his fashionable haircuts. I'm sure most of you remember hearing about him during the evolution and phylogenetics lecture. So the principle of inclusions states that the clasts or pieces within a rock are older than the rock itself. So on the left, we have a rock called a conglomerate, and you see giant hunks inside that big rock. Those hunks are older than the rock itself. On the right, we have a piece of amber. The insect is inside the amber. The insect is the clast. It is older than the amber itself. But that concept might be a little confusing. So let's bring this back to something we like a little bit more than geology, cookies. All right, I'm assuming. This idea says that the cookie is younger than the chocolate chip. So let's go to the store. We're going to buy stuff to make chocolate chip cookies. So we buy flour, we buy sugar, eggs, butter, and we buy a bag of chocolate chips. We throw those chocolate chips into the cookie dough, and then we bake the cookies. The chocolate chips had already fully formed by the time we bake the cookies. Therefore, the chips are older in the age than the cookie. So the principle of inclusions could just think about it next time when you're doing your assignments. Instead of thinking about rocks, you can think about it in terms of chocolate chips, and that might help you. All right, William Smith. William Smith is an interesting person. He was born fairly in the lower class in the United Kingdom, but he loved geology, so he actually spent a significant amount of his time and money making some of the first geologic maps of the United Kingdom. So faunal succession is something he came up with while he was making his maps. Faunal means animal, succession means changes through time. So what his idea is that fossils contained in specific rocks, layers of rock, will change in a very predictable pattern, meaning we know where we're going to find T-Rex fossils. T-Rex, the dinosaur, is found in the Cretaceous. We know where we're going to find certain types of fossils. All right, so here's an example of trilobite fossils. We'll learn more about these later, but all you need to look at here now is to see that the bottom here, Lower Cambrian, to the top, Mississippian Permian, you see changes in those trilobites. That's faunal succession. And again, here is our geologic timescale. The oldest is on the bottom. What principle is that? I'm assuming you said superposition. You'd be correct. All right, so again, to sum this up, these principles are going to be really useful for us figuring out the order in which rock layers were formed. This brings us to lithostratigraphy. Stratigraphy means layers, litho means rock. So now we're going to be studying the rock layers to understand ages, using Steno's principles and Hutton's and everybody else's. So to do this, we're going to be looking at cross sections of rock. Cross sections of rock kind of look like the slices of a layered cake. All right, here's an actual geologist who's looking very excited to be in front of a cross section of rock. All right, so superposition, which one is the oldest? The red layer, or number 7, depending, all right, on which one you're looking at, but it's this one right here. It's on the bottom. All of these slides have the answers to them, so you can go through this at your own pace using the slides on Canvas. Original horizontality. Rocks are not likely to be deposited in this strange manner, tilted up. So which one is the oldest? Oops, sorry. So if we're looking at this one here, this dark green layer at the bottom, is likely to be the oldest. If you rotate these layers back in your mind to being flat and horizontal, that green one is closest to the bottom. Now, cross-cutting relationships. When did the fault, and the fault is just a line that separates two bodies of rock, they've been shifted by movement. So the fault is shown by this black line cutting across. When did it form? First or last? Just like the example with the construction paper, when we cut through it, that has to happen last. So the fault formed last. Now, let's figure out types of faults, because there's two types of faults here. There are reverse faults and there's normal faults. So to understand this, it's pretty simple if you follow the tricks I give you. There are two pieces to a fault, a hanging wall and a foot wall. To understand the difference between the two, draw yourself a little stick figure person. Have it standing straight up, like it's, in a picture standing normally, all right? Across that black line here. So what we see here is the head, the H, head, falls in the hanging wall, H, H. The foot falls in the foot wall, foot, foot, all right? So there's your directions there. You draw your stick figure. The head will always go in the hanging wall, foot will always go in the foot wall. So in a reverse fault, the hanging wall will move down, right? These are rocks, they're moving around. A reverse fault means that hanging wall will shift up, all right? A reverse fault means that hanging wall will shift up, all right? In a normal fault, the hanging wall will move down. Now think about it this way. The theory of gravity states that everything's being pushed down, right? You're not actually just sitting in your chair right now. Gravity is holding you in your chair. So if you think about it, a normal movement of rock should be moving down. So in a normal fault, we think the hanging wall moves down. Reverse moves up. So in this case, let's match up the layers to see how that hanging wall has moved through time. So you see layer 7, which is right here, and you see layer 7. Though it's the same layer. here's the hanging wall. The hanging wall has shifted down to its current position, meaning it's a normal fault. All right. So now unconformities. These represent missing time in the rock record. To conform means to fall in line, to follow a certain pattern, to do something a certain way. To unconform means something is missing, and what's missing in this example is time. They occur for a number of reasons, but imagine with me every single bit of sand that has ever been made on Earth. Not all of it is always preserved. Some of it is destroyed. Some of it just doesn't get put down into the rock record. The reasons for that can vary. For example, we could have a hurricane like Irma that blew away a bunch of sand. We could have a giant earthquake. We could have plates crashing together through the theory of plate tectonics, and we could destroy some of that record. Okay? So, sometimes this happens. So, these are generally represented by a squiggly line. So, if you look here, between 7 and 9, here's 7, here's 9. We have this nice purple layer 10. Let's say something weird happens to layer 10. It disappears. We mark it with a squiggly line. So here is the first unconformity ever found, or ever named. Hutton found it, okay? And this is Sicker's Point in Scotland. It's an incredibly famous vacation spot for geologists. But you see here that this rock here and this rock here are totally different. See how they're changing directions? This rock is pointing straight up. This rock is going from side to side. That is indicative, meaning likely showing an unconformity, meaning something between those two is missing. So this brings us to our last concept, law of facies. When environments, meaning a beach, a river, an ocean, something like that, are preserved in the rock record, they stack vertically, just like the cross sections you've been seeing. So let's say we have a beachfront. In the geologic record, we'd see the beach, we would see shallow ocean water, then we'd see deeper ocean water. If the water was rising, we would see that. And what this means is you should be able to read the rock record like a book, from the start of deposition, meaning the start of stuff being put into the rock record, to the end. Could this ever be incorrect? Walther's law of facies, are there situations where we can say that that will not work? Absolutely. If you were thinking unconformities, you would be absolutely right. So an unconformity means there's missing time. Now let's say if we're reading the rock record like a book, there's an unconformity. Let's say this is Harry Potter. I'm assuming most of you have read Harry Potter. If you haven't and don't want me to spoil anything, mute the microphone for a few minutes, okay? Like 30 seconds. So Harry Potter, he finds out he's a wizard. You know, Hagrid comes in and he goes, Harry, you're a wizard. That was my best Hagrid voice. And then all of a sudden, boom, Voldemort's back. You've missed some stuff, haven't you? You haven't read things fully. Things are missing. And it's going to be confusing because you're going to say, hey, what now? How do we know? What? How did this just happen? So an unconformity can violate Walther's law of facies. Now, I know we said we spend most of today talking about sedimentary rocks, but we will be talking about extrusive or volcanic rocks too. They can also form in layers. So here is a lone geologist working in volcanic rocks out in the west. And you don't need to worry about these names, intrusive and plutonic. We're not going to worry about them in this class. But essentially what can happen is they can actually cut through other rocks as well. So these rocks, igneous rocks, can often follow the patterns of stratigraphy as well. And these are useful for radiometric dating, which is another way to say absolute dating, meaning getting a full age. And we're going to use that in combination with our relative dating to create a full geologic timescale. So here is an example of igneous rocks. The igneous rock here is represented in layer 1, which is that triangle-shaped piece. Everything here is following a pretty clear pattern, okay? So we have the bottom here, which is number 7. On top of it, we have number 11. Then we have number 9, 6, 5, 10, and then 1. Why is 1 last? 1 is last because of the principle of cross-cutting relationships. 1 is cutting across all of these other layers, so it must have come last. So let's try another example. In this one, I want you to follow along with me, pause this for a second, see if you can figure it out, and then I'm going to walk through it with you. So pause the video. All right. So our first layer here is this brown one right at the bottom, and that is due to the principle of original horizontality and due to the principle of superposition. Then we move to the purple, the yellow, the green, the brown, the black, the magenta, and the blue. Okay? So now what's the next layer? Pause the video for a sec. Okay, so the next layer is a squiggly line here. And the squiggly line has a very special name. It is called an unconformity. Now we're going to move to this next top layer. Which is going to come first? The green layer or the stuff inside the green layer? Due to the principle of inclusions, the stuff inside the green layer, and these are fossils, these are called Gryphea, and not that you need to know that, but due to the fossils inside of it, those fossils formed first, the rock formed second. So that green layer comes after those fossils. And then we've got the yellow layer. Now we have our red layer here, and this is because of the principle of cross-cutting relationships. It stops before it comes to this yellow line up here. And now we've got, or not yellow, orange, excuse me, the orange and the blue. So rewind that, go through it a couple times, make sure you understand it. Now, using rock layers to figure out how old something is not the only way to do it. We can also use biostratigraphy. If lithostratigraphy means using rocks, litho, to understand layers, bio is using what? Fossils, living things. That's what bio means. So we're going to use fossils to figure out how old things are. Okay, so for example, if I am standing in Montana and I find a T-Rex skull, and then someone in South America finds a T-Rex skull, you can know that they're standing in approximately the same layer. And now this wouldn't happen because T-Rex is actually just found in North American stuff, but let's pretend. Okay, so in index fossils, we're going to use index fossils to understand that. And what an index fossil is a very special type of fossil that is only preserved in certain situations and makes it useful for understanding how old something is. So, traits of a useful index fossil. It needs to be abundant. And the reason for that is if you were a paleontologist and you could only find one or two examples of a fossil, you're not going to be able to use it to learn a lot about how old other rocks are. So pollen. Most of you who have spent more than 5 minutes in Florida already know that pollen is pretty abundant, right? So pollen is an excellent example of an index fossil. You can find pollen pretty much anywhere, especially in the rock record. It needs to be easily identifiable. What that means is it needs to have features that make it clear to a scientist what it is. It needs to be widespread geographically, meaning if I find a fossil that only exists in Florida, that's not going to be very helpful to me because I need to also date the stratigraphy in China or India or Pakistan. We need to have it geographically widespread. It needs to be independent of environment. What I mean by that is that organisms have to live in a variety of types of places. And then finally, they need to have a narrow stratigraphic and temporal range. What that means in normal person words is that they needed to have lived for a very short time. Imagine with me if you found a fossil that lived for 100 million years. Anytime you found that fossil, you'd only be able to say it's within 100 million years. That's not very useful. We want to get smaller than that. So say we found a fossil that only lived for about 10,000 years. That's pretty darn good. 10,000 years is a pretty short amount of time geologically. So while rock layers may not always look the same, let's say these rock layers are real, and that yellow on the left-hand side with the fossils in it, let's say that yellow one turned yellow because of some weird chemicals. It's still preserved at the same time as this orange one here, but they look a little different. So if we have these teeth here, we can make another judgment and say, well, maybe these are the same time. Okay, practice the video, or pause the video. I want you to go through this example and see if you can figure it out. Just as a word of wise here is the letter J on this one. A lot of people miss that. Okay, so go through that. Pause the video. All right. So hopefully you put H down at the first, right? As you can see, A cuts across a bunch of stuff, so it doesn't belong first. We have H. Oh, excuse me, not H. I'm sorry, I was looking at that wrong. E, right there at the bottom. We have G forming on top of it. We have E, G, then we have L, then we have C. Then we notice what's cutting across all of these layers? H. Then on top of that, we have M, D, J. You see that A stops right at J, so A comes next. N, K, B, F. Make sure you understand why that is. So if you're really feeling ready to tackle this problem, try this one. It's kind of fun. All right, this one's the hardest one you'll ever do in your entire life. So if you can get this one, then you have aced the concept. Now, arriving at absolute dates. Human history is a tiny piece of all of Earth's history total. Written histories only go back for a short amount of time. They don't go back very far, especially when you consider how old the Earth actually is. So here is an example of geology and art history combining. This is The Scream, a very famous painting by Edvard Munch. And one of the ideas out there for this painting, this shouldn't say theories, this should say speculations, okay, my bad, is that Edvard Munch saw a volcano erupting. This is the famous Krakatoa eruption. It was one of the largest volcanic eruptions in the world. And he was living, this happened in Southeast Asia. He was living in Northern Europe at the time. That's where he was born and raised. And he saw the sky turn red from that volcanic explosion, and it haunted him. So that's one of the ideas about why he painted that. We have a couple other ways of getting our absolute dates. So one of these could be considered magnetostratigraphy, using magnets. So the Earth has a magnetic field, and our poles, the North Pole and the South Pole, actually swap positions. We're not the only solar system in the body that does this. We'll learn more about this during Plate Tectonics Day. The sun actually does this every 22 years. So the north becomes south, south becomes north. The lines actually point differently. But what this means is we can find these patterns of polarity when north means north, or when north is pointing at the north, or when north is pointing south, and we can make these global patterns to understand what's actually going on. We can use trees. Trees grow in annual rings. Oldest is at the center, youngest is just by the bark. We can actually get ages from trees. The oldest tree on Earth is about 5,000 years old, the Great Basin bristlecone pine. However, this is incredibly precise. I can actually tell what year had more rain than others. We can tell a whole lot from this, but it only goes back about 11,000 years. And if you remember, the Earth is approximately 4.5 billion years old. So, oops, I got ahead of myself. How do we figure out how old the Earth was? We're going to start with Lord Kelvin here. Lord Kelvin is one of the first scientists that we know of who wrote down his ideas on how old the Earth actually was. He thought it was between 20 to 400 million years old. So he's off by quite a lot, but it's still a lot longer than the couple thousand years we originally thought. So you don't need to remember his name. He didn't understand radioactive decay, though. Decay adds heat to the Earth, and what he did was he calculated how much heat the Earth lost every single year to get an age. He didn't understand, though, that the Earth's heat replenishes. So, that brings us to Becquerel, who's a French physicist, and he discovered radioactive decay in 1895. He won the Nobel Prize with Marie and Pierre Curie. Now, radioactive decay is based on the idea of an isotope. An isotope is an atom of a single element which varies in the number of neutrons. So, an element has neutrons, protons, and electrons. Protons have positive charges, neutrons have neutral, electrons have negative. All elements have the same number of protons. Okay, that never changes. Hydrogen always has one proton. However, hydrogen can have different numbers of neutrons. It can actually have 2 or 3. 3 neutrons in hydrogen is something we call deuterium. Fun fact of the day. Some isotopes are naturally unstable, and then it will start radioactive decaying. The radiation is what's emitted from the breakdown of our unstable isotopes. Now, not all of them are harmful. So you see radioactive decay in superhero movies, right? I think the Hulk was an example or something like that, right? You get superpowers or supervillain powers. That's not how it works. Everything around you is decaying, okay? So carbon-14 in living organisms decays. So if something dies, like a plant, it will actually start decaying. That's not dangerous. So when this happens, we start with the original isotope. For obvious reasons, we'll call this original isotope the parent. Once it starts changing, it emits radioactive decay. It releases daughter isotopes and heat. So we go from the parent to the daughter with heat release too. Rutherford understood that there's a certain rate at which radioactive decay happens. So this is what we call the half-life. And a radioactive half-life literally means how long it takes for half of a parent isotope to change into a daughter. So this happens at a very steady rate. Okay? And we know the half-life of almost every element known to man. All right? So no matter the amount of parent isotope or the type of element present, over half will decay into daughter over a certain period of time. So here we have 100, and then we can go to 50, then we can go to 100 to 50, all the way down to 25, 12.5, 6.25, 3.75, so on. So, different radioactive isotopes have different half-lives. So here's an example, or here's just a breakdown. So if we have 50% parent, we've had one half-life pass. So 100 to 50. We've done that equation once. So then, if we have 100 down to 50, down to 25, that's 2 half-lives. 3 half-lives would be to divide that 25 into 12.5. So as you can see, this continues down and down and down. Here's an example. An isotope has a half-life of 2,700 years. 2,700 years. You find a sample with 25% of the original isotope left, the parent isotope. How old is that sample? Well, if it has 25% of the parent isotope left, then there's 75% daughter, right? 25 plus 75 equals 100%. So if 100 to 50 is 1 half-life, 50 to 25 is 2. 2 half-lives have passed. 2,700 years times 2 half-lives is 5,400 years old. Here are some geologically useful radioactive isotopes. You do not need to memorize this list, but as you can see, there's a wide range in how long it takes certain things to break down. Rubidium strontium takes almost 50 billion years. Carbon dating is 5,730 years. Many people have an argument that radioactive dating doesn't work because carbon dating doesn't work very well for things that are very old. Of course it doesn't. Look at its half-life. After 70,000 years, there's only so much isotope left to be able to measure. So we generally don't use carbon dating for things that are very old. About 70,000 years is our general cutoff date. All right, so how this works is C12 and C14 occur in predictable rates in everything that's living. It occurs in you, it occurs in that tree in your backyard, that squirrel that stole your sandwich the other day while you were sitting on USF's campus. Everything. C14 decays into nitrogen-14, usually once an organism starts decaying from death. So, here's an example of the McClung Museum is a small natural history museum in Tennessee, North Carolina. And Tennessee, North Carolina has a strong Native American history. We're actually able to carbon date many of the artifacts that have been found or that have been kept in indigenous cultures through hundreds to thousands of years. So radiocarbon dating can tell us how old many of these artifacts are, but usually only if it's younger than about 70,000 years. Older than that, not enough to measure. So if we've got radiometric dating and we've got relative dating, now we can start making really good inferences about how old things are. So, question for you. I have a layer, number 2, here on the bottom. This is 5 million years old. This layer is 3 million years old. How old is this layer here, blue layer? How old is that layer? If this is 5 and this is 3, how old is this? You might be tempted to say something like right in the middle, 4 billion years, or 3 million years. But would that be accurate? Do you know that all of these layers lay down at the same rate? You definitely don't know that. So the correct answer is between 3 and 5 million years. So this is how we made our geologic timescale. These rocks are based on changes we see in the rock record. Or these terms are based on changes we see in the rock record. So if you look at this, you see unfamiliar words to you like Ordovician, Cambrian, Silurian, Devonian, Hadean, Archean, Paleoproterozoic. Big, weird words. All of these are based on changes we see, generally in the fossils. Do not write this down. There is no need, but I'm going to go through it with you really quickly. The largest unit of time is a super eon, then eon, era, period, epoch, age, chron. Super eon, the Precambrian, 4.56 billion years ago to 542. There are 3 eons here. The Hadean, literally named for the god of the underworld, Hades. The Archean, first evidence of life all the way down to eukaryotes, something that you are familiar with because you are one. And then to the Proterozoic. First eukaryotes all the way to organisms with shells 542 million years ago. Phanerozoic is 542 million years to literally this whatever day you're listening to this Friday. Contains 3 eras. The Paleozoic, the Mesozoic, the age of the dinosaurs, Cenozoic, the era we're in right now. All right, so here are your review questions. I will see you soon. Thanks for listening.